Hello, this is Mason Haggerty with question 13.6 from Fundamentals of Heat and Mass Transfer by Bergman. This question states, the cross-strings method of Hodel provides a simple means to calculate view factors between surfaces that are of infinite extent in one direction. For two such surfaces, A, with unobstructed views of one another, the view factor is of the form factor 1, 2 equals 1 over 2 width 1 times AC plus BD minus AD plus BC. So we can see here in the diagram how they have it laid out, where width 1 is the width of the bottom plate, and you have corners A, B, C, and D, and surfaces with area 1 and area 2, though you don't use the area. So we can then look at part B, which is where the question actually starts, and we can see that it is two parallel plates, 4 meters wide and 1 meter apart. And again, this is extending infinitely into and out of the page. So for this, again, we use that equation that was just given, and we know that the width is 4 meters. So you get that the view factor is equal to 1 over 2 times 4 meters times, and here you're doing AC. So again, that's from the bottom right corner to the top left corner. So for this, it's going to be, you just use Pythagorean theorem. So you get the square root of 4 squared plus 1 squared, which is going to be equal to 17 squared. But then you also have add in BD, which is the exact same, and that's from, again, the bottom left to the top right corner. So you're going to end up with 2 times the square root of 17 meters. And then you subtract out AD plus BC, and that is basically just from the corresponding corners on each plate, and because they're one apart, you know that it's going to be 2 meters. So your final equation is 1 over 2 times 4 meters times 2 times the square root of 17 meters minus 2 meters, which equals 0.781, and that is your view factor for B. Next, for part B, we're looking at this kind of right angle. For this, it is a little bit weird to define your corners, but again, A and B are going to be the exact same position, and basically just imagine that this was a parallel plate that was rotated 90 degrees, so your C is overlapping with B, and your D is sticking straight up there. So for this one, again, we're going to use the width of the bottom plate, so you're going to get 1 over 2 times 4 meters, and then you're going to multiply this by AC and BD, but again, because C is at the same point as B, which is in that bottom left corner, the distance is actually just that 4 meter width of A1, and your B to D, because again, D is the top left corner, is going to be just that 1 meter height, so it's just going to be 4 meters plus 1 meter, which gives you 5 meters, obviously. And then you subtract out the distance from, again, AD to plus BC, and AD, we can see that is, again, Pythagorean theorem, and so for that, you're once again similar to a question or part B, you're going to get square root 17 meters, and because BC, they're overlapping, you get 0 meters. So solving this equation, you get a view factor of 0.110. Next, for part D, this is where it starts to get a bit more complicated, but really the hardest part of this question is just defining your coordinates, basically. So for this, I pulled the diagram out here, and as you can see, I defined each corner, A, B, C, and D, and then I wrote basically just what the coordinates are for C and D, because A and B are pretty obvious. They are just, 4 and 8 meters at 0 y. But for C and D, it's a little bit more complicated. Basically, you have the hypotenuse and you have the angle, so you just need to now find the adjacent side and the opposite side just using trig. But for this, going through the trig, again, I've written it all out here if you want to look at it. You get that C is located at 3.46 x and 2y, and D is 6.93 x and 4y. So from this, now you can create your equation for the view factor, which again, we're using that width of that bottom plate A1, which is 4 meters. But then for each of these, again, for AC, BD, AD, and BC, you're just going to be doing the Pythagorean theorem between each of these points. So because you now have the defined coordinates for each one, you basically just do the Pythagorean theorem for each one. So for example, for AC, it's the square root of the x location of A, which is 8, minus the x location of C, and then you square that, plus the y location of A minus the y location of C squared, and you repeat that for BD, AD, and BC. Doing all that, you get this equation here, and that gives you a view factor of 0.463. Next up, part E. This is a little bit easier than part D actually, but it's the same idea. So again, I went ahead and looked at this, and I decided that A, B, and C are all pretty straightforward, so I didn't list them, but D is a little bit complicated. Once again, you're just doing the kind of same trig coordinates, where you're just doing 4 cosine 30 and 4 sine 30 to get the x and y location of D, which in this case is 3.464 in the x and 2, so that's basically the same as point C actually in the previous part. And from this, you can then once again make your equation where the view factor is equal to 1 over 2 times the width of A1, which is 4 meters, multiplied by 4 plus 4, and then subtract out the square root of 4 minus 3.464 squared plus 0 minus 2 squared. And then this is added, to this is added 0 because B and C are overlapping, and this gets you a view factor of 0.741. So basically for this method, you can just define everything as a coordinate, and then from there you're just setting up this equation using the Pythagorean theorem between all of the points. And so for this, I just for the sake of it, made a little MATLAB script that lets you kind of repeat this. So you can see that here. This isn't for the question. This was just because it makes it a little bit easier if you wanted to do future view factors. So I basically just defined all of the coordinates for all of the different cases. And then, as you can see down here, I created a function which basically just defines AC, BD, AD, and BC as the respective equations, which is, again, just the Pythagorean theorem between all of the points. And then it just finds the view factor using all of those variables and the equation given. And so for each of these, I plug in the coordinates and then run the function, and it verifies that the view factors calculated above are correct. And this gives a little bit more precision. And of course, there's probably more elegant ways to do this, but this was just really quick to write up. And I can plug in now any 4 coordinates, and it provides an output of the view factor. So